Lake ice does not simply freeze in one place and remain still all winter. It expands and contracts as temperatures change. It may bond to pilings and frames. Changing water levels can move the ice vertically. Wind can drive large sheets toward the shore. Currents can move broken ice beneath the surface, and during spring breakup, thick slabs may pile against anything in their path. A dock can therefore experience forces from several directions: horizontal pressure, vertical uplift, twisting, impact. Repeated freeze and thaw movement. A piling may be strong enough to support the dock vertically, but still bend when ice pushes against it sideways. A connection may survive one winter but loosen slightly. The next winter, that loosened connection transfers more load to nearby braces and fasteners. That is how small seasonal movement becomes progressive structural failure. Design number 1, a seasonally removable dock. The most reliable way to protect a dock from moving ice is straightforward. Remove the vulnerable structure before freeze-up. This includes lightweight floating docks, wheel-in docks, roll-in docks, and sectional docks that can be disconnected and stored on shore. A dock that is not in the water cannot be crushed by expanding ice. That makes seasonal removal especially effective on smaller lakes, shallow shorelines, and properties with enough storage space. But removability must be designed into the dock from the beginning. Consider section weight, connection type, shore access, winch or wheel systems, storage location, electrical and water connections, the number of people needed for removal. A dock that technically comes apart but requires heavy equipment every fall may not be practical. The best removable systems use manageable sections, accessible hardware, and a repeatable removal process, and probably learning about some new neighbors. Design number 2, a lift-out or raised dock. Where full removal is difficult, some docks can be lifted above the expected ice zone. A lift-out dock uses cables, winches, pivoting frames, or support towers to raise the deck and framing before the lake freezes. The objective is to leave as little structure as possible in contact with the ice. This can work well for lightweight aluminum docks and certain hinged shoreline systems. But raising only the deck is not enough when permanent pilings, legs, or braces remain in the water. Those remaining components must still resist ice forces. The lifting mechanism must also be designed for the dock's weight and balance so the frame does not rack during operation. Before choosing this approach, confirm the required lifting height, the expected ice elevation, the stability of the raised structure, cable and winch capacity, wind exposure, and whether the pilings remain vulnerable. Design number 3, a flexible floating system. A floating dock can move with normal water level changes instead of resisting them. That flexibility can reduce some vertical stresses, but it does not make the dock immune to ice. A floating dock left in place can still be pushed toward shore, trapped beneath an ice sheet, crushed against fixed pilings, damaged at hinge points, twisted by uneven freezing, pulled away by moving ice. A winter-capable floating design should include controlled movement. That may involve sliding pile guides, flexible utility connections, articulating gangways, heavy-duty hinges, replaceable connection components, adequate clearance from shore and neighboring structures. The dock should be able to move vertically without becoming wedged. It should also be restrained so it cannot travel uncontrolled across the lake. This strategy works best where local ice movement is limited and the dock system has been specifically designed to remain in the water. Design number 4, deep brace, low exposure pilings. When a permanent fixed dock must remain in place, the support system becomes critical. The goal is not simply to use the largest piling available. The goal is to create a load path that transfers ice forces safely into the structure and lake bottom. Important design considerations include adequate piling embedment, appropriate piling diameter, cross bracing, strong beam-to-pile connections, corrosion-resistant hardware, limited exposed surface area, proper spacing, local soil conditions. A shallow piling can rotate or pull loose. A tall, unbraced piling behaves like a long lever, and a large solid frame located directly in the ice zone gives the ice more surface area to push against. Rounded pilings generally allow ice to flow around them more easily than wide, flat structural faces. Bracing can reduce movement, but braces placed directly within the active ice zone may also become additional contact points. This is where site-specific engineering matters. A dock on a sheltered pond does not experience the same winter loads as a dock facing miles of open lake. Design number 5, ice releasing and breakaway connections. Sometimes the weakest component should be intentional. That may sound wrong, but a controlled, replaceable connection can prevent damage from spreading into the most expensive part of the dock. For example, a removable gangway connection may release before the gangway tears the main dock frame apart. The sacrificial connector may fail before a floating section pulls permanent shoreline supports out of alignment. This concept is similar to a fuse in an electrical circuit. The replaceable component protects the larger system. Possible applications include removable hinge pins, breakaway utility connections, replaceable shear bolts, seasonal gangway removal, independent dock sections, flexible anchor connections. These components must be selected carefully. An improvised weak connection may create a drifting dock, submerged debris, or a public hazard. Breakaway systems should be engineered so that failure is predictable and the release section remains secured. Design number 6, bubblers and propeller de-icers. The sixth strategy does not change the dock frame. It changes the water around it. Two systems are commonly discussed, air bubbler systems and propeller-style circulator de-icers. Although people often use the names interchangeably, they operate differently. A bubbler uses an air compressor connected to a perforated hose or diffuser located below the surface. Air bubbles rise through the water column. As they rise, they encourage water movement and may bring relatively warmer water upward from below. The moving water can reduce ice formation in a controlled area. Bubblers are often useful where the goal is to protect a long, narrow section of dock or several pilings. A propeller-style de-icer uses an electric motor and a submerged propeller to circulate water. The unit can be suspended vertically or mounted at an angle. Its position and direction strongly influences the shape and size of the opening. A vertical orientation generally creates a more concentrated opening. An outward angle can send moving water farther from the dock and create a much larger area of thin ice or open water. Warren County, New York advises property owners to create a narrow open water area around the dock and warns that angled circulator units can open elongated areas extended away from the structure. More open water is not automatically better. The goal is to relieve damaging ice contact around vulnerable structural components, not to keep a large section of the lake ice-free. So how to position a de-icer. Placement matters as much as the equipment itself. A poorly positioned de-icer may protect one piling while directing moving water toward another vulnerable area. It may also create open water far beyond the dock. The protected zone should normally be concentrated around the components where ice contact would cause damage. Depending on the site, that might include pilings, float corners, hinge connections, boat lift legs, shore connections, utility risers. Avoid blindly aiming the flow toward the middle of the lake. The Warren County guidance specifically recommends keeping the opening narrow and positioning circulator-style equipment vertically rather than angling it outward when a broad opening is unnecessary. The ideal depth and angle depend on water depth, temperature profile, current, dock shape, bottom conditions, ice thickness, manufacturer instructions. Follow the equipment manufacturer's installation requirements and check local regulations before operation. De-icer safety. A de-icer deliberately weakens or removes ice. That makes warning and access control essential. Someone approaching from the lake may see snow-covered ice without realizing that the ice has been thinned from below. The hazardous area can extend beyond the visibly open water. Use highly visible warnings around the affected zone. Consider reflective signs, warning lights where permitted, ropes or barriers, neighbor notification, regular inspection, ground fault electrical protection, marine rated wiring and connections, a timer or thermostat controller, immediate shutdown if equipment moves or fails. Never assume the ice near an operating bubbler or de-icer is safe for walking, skating, snowmobiling, or vehicle travel. Local rules may regulate a de-icer operation, warning signs, electrical installations, noise, or the amount of open water that can be created. Common de-icer mistakes. Mistake number 1 is creating too much open water. A larger opening wastes energy, increases the safety zone, and may affect neighboring properties. Mistake number 2, aiming the current away from the dock instead of concentrating protection around vulnerable components. Mistake number 3 is installing equipment without considering changing water levels. A unit that works properly in December may become too shallow, too deep, or incorrectly oriented later in the winter. Mistake number 4 is ignoring electrical safety. Water, ice, damaged cables, and improper shore power connections are a dangerous combination. Mistake number 5 is treating a de-icer as a substitute for structural design. A power outage, tripped breaker, blocked propeller, damaged airline, or severe weather can stop the system. The dock should not depend entirely on one piece of equipment to survive. And mistake number 6 is failing to inspect the system. Winter equipment should be checked regularly from a safe location. Look for changed water patterns, loose mounting hardware, shifted equipment, damaged cords, excessively large openings, noise or vibration changes, loss of airflow. Which design is best? Well, here is the practical answer. For a small seasonal residential dock, removal before freeze-up is usually the lowest risk strategy. For a lightweight dock that cannot be stored, a lift-out design may keep most of the frame above the ice. For a floating dock left in place, controlled vertical movement and flexible connections are critical. For permanent fixed docks, deep support, proper bracing, strong connections, and reduced ice exposure become the priority. Where one component could pull the entire dock apart, engineered sacrificial or removable connections may limit the damage. And where ice bonding around pilings remains a concern, a properly designed bubbler or de-icer system may provide additional protection. These strategies can also be combined. For example, permanent main pier may use engineered pilings. The gangway may be removed. The floating platform may use sliding guides, and a small bubbler may protect the remaining fixed supports. The best design is rarely one isolated product. It is a complete winter plan. There is no universal dock that can survive every possible ice condition. Ice thickness, water level changes, wind exposure, current, lake shape, soil, dock orientation, and local climate all matter. But the 6 strategies we covered can significantly reduce risk. Remove the dock. Lift it above the ice. Allow controlled movement. Engineer the pilings and load path. Use controlled release connections. And, where appropriate, manage ice contact with a bubbler or a de-icer. The biggest mistake is waiting until the lake begins to freeze before developing a plan. Winter protection should be considered when the dock is designed, not after the first cracking sounds are heard beneath it. Before installing or modifying a permanent dock, consult local authorities and a qualified marine contractor or engineer familiar with your lake. And before operating a bubbler or de-icer, confirm the electrical requirements, local rules, warning requirements, and manufacturer's installation instructions. A dock that survives winter is not protected by luck. It is protected by preparation. If this video helped you understand winter dock design, subscribe for more practical videos about docks, boating infrastructure, waterfront construction, and marine engineering. And in the comments, tell us what happens on your lake. Do you live on a lake that freezes during the winter? Does the ice stay in place, rise and fall, or move toward the shore? I'm really curious. If you would like a copy of the dock checklist, please send me an email to pj@pennyvaledocks.com. And if you'd like a copy of this blog that goes with this video, I'll send one of those also. You just got to ask. Thank you.